Hello everyone and welcome again to another of my climate change debunking presentation series. In this presentation we will be uh, paying special attention to thermodynamics and using thermodynamics to debunk climate change. As you can see from the topic, Earth, the great open thermodynamic system, I will show without a shadow of a doubt that heat is not being built up in the Earth's atmosphere to the point where it becomes an existential threat. This video will show that heat, just like any other properties are in the Earth climate atmosphere, is recycled and move around and changes, and it doesn't build up to the point where it becomes a danger to us. So sit back, relax, and enjoy another episode of my debunking series. Thank you. We will now define thermodynamics. Thermodynamics is a combination of two words. First, thermo, which means heat, and two, dynamics, which means related to, and is characterized by the constant change, activity, or process within a system. Therefore, thermodynamics directly means the constant change, activity, or process of heat in a system. As you can see from the diagram on your right, the system is in dotted line, and which is the boundary of the system, and outside is the surrounding of the system. So thermodynamics has to do with the interchanging of heat between the surrounding and the system. In this in this slide, we'll be looking at the types of thermodynamic system, and as you can see, the Earth is considered to be an open thermodynamic system. We have three types of thermodynamic system: isolated, and closed, and open. Here you can see in red the exchange of energy and the exchange of matter within that thermodynamic system. The Earth is considered an open thermodynamic system. Heat enters Earth's atmosphere and surface from the sun and from geothermal energy from the Earth core. Excessive heat produced during the day leaves the Earth's surface and lower atmosphere and is dispelled to the cold upper troposphere or higher atmosphere altitude. Heat is conserved by the atmosphere component during the night and winter, making life on Earth possible. Heat moves and is distributed around the Earth via sea and air current. And finally, matter enters surface via asteroids and volcanic eruption via helium gas. So therefore, as you can see, the Earth is an open system, open dynamic system. We will now be looking at the laws of thermodynamics, and as you look at to your left, you see there is actually three laws of thermodynamics. One called is the zeroth law, which is fairly new, a fairly new addition to the laws. But these more or less four laws dictate the following with heat. For heat, laws of thermodynamic control and direct thermal energy, also known as heat generation, storage, preservation, transfer, conversion, and release and use. So the law of thermodynamics control the movement, everything to do with heat, And for instance, in the first law of thermodynamics, you can see the conservation of energy, where it says energy can 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 change form, but is never created nor destroyed. In this sense, heat, when for instance when heat is taken up into the atmosphere, it is spread out among the colder gases. That's it's in the upper atmosphere, and therefore it's not destroyed, but it is dissipated and used. It is dissipated and used up. So it's not destroyed. It is not destroyed. It is dissipated. And for instance, look at the second law, entropy of one system always increases, meaning that the entropy has to do with the orderliness of a system. So as soon when the temperature is hotter, the air moves faster, and as the air gets colder, it moves slower, and so therefore there's less disruption, less entropy in the system. And this is the law that cover that factor. So as you can see, thermodynamics actually controls, again, just to reiterate, control and direct thermal energy. In a discussion into climate change, we'll have to take into consideration the atmosphere. And in this slide, we'll be looking at what the Earth atmosphere is, really. The Earth atmosphere consists of 5 layers of varying height above sea level. Each layer plays a significant role in the preservation of life on Earth. For example, in the stratosphere is where you'll find the ozone layer, which is instrumental in stopping some of the sun's deadly radiation from reaching the Earth's surface. The closest and most important to us is the troposphere, because it is this layer that has the most of the air vital to our survival, and is where all the weathers and climatic events occurs. As you can see from the diagram on the left, you have the troposphere is also where the level where the plane air travel take place, and that's why it is most important that we understand what this level contain. In this slide, we'll be looking at the troposphere in a little bit more detail. And as you can see, tropos means change. This layer gets its name from the weather that is constantly changing and mixing up the gases in this part of our atmosphere. This layer has the air we breathe and the cloud in the sky. The air is densest in this lowest level and get progressively denser as the sea level is approached. The troposphere is bounded by the tropopause and then the stratosphere directly above it. Nearly all water vapor reside in the troposphere, but the proportion of water vapor in the troposphere decreases with altitude. This is why water vapor content is normally greatest near the surface of the Earth. In the troposphere, temperature decreases with altitude. At the top of the troposphere, the temperature can reach -50 degrees Celsius. This is where most of the commercial airplane flies. And to let it know that most of the heat, that is the excessive heat that is produced by the sun interaction with the surface of the Earth, is dispelled up in the cold troposphere. In this slide, we'll be looking at the air composition of the troposphere, and as you can see by percentage of volume, nitrogen is the most voluminous gas, followed by oxygen, which is almost 21%. So together, oxygen and nitrogen consists of almost 99% of the air composition. Argon followed by a 0.934 percentage, and then carbon dioxide at 0.34, 0.37 to 0.3 to 0.4, depending on who's quoting the figures. But it's around about that. And then you have the other trace gas: neon, helium, methane, and krypton. But as you can see, the main gases that for our consideration here is nitrogen, oxygen, and as you can see, the other 1% of gas, of which carbon dioxide is considered a trace gas, is carbon dioxide, neon, helium, and krypton, methane. So here we'll take a look at heat, because it's all about heat, and we need to understand what exactly is heat and how is it relevant to our discussion. Heat is the result of kinetic energy, energy of motion in a substance, atom, molecules, ion, in solid, liquid, and gases. The more kinetic energy these molecules, atoms have, the hotter the substance will be. Heat is transferred via 4 methods: 1. Conduction, 2. Convection, 3. Radiation, and 4. Evaporative cooling. Earth receives most of its heat from thermal energy from the sun incoming infrared radiation interaction with matter on the surface of the earth, i.e., for example, rocks, building, water, tree, soil, and sand. These are just some of the few material that the earth incoming solar radiation interact with to create heat. The sun incoming infrared radiation does not directly heat the nitrogen, oxygen, and carbon dioxide in the atmosphere. Contrary to what is told, the sun incoming infrared radiation does not directly heat nitrogen, oxygen, and carbon dioxide in the atmosphere. They are heated via conduction by their intimate contact with the Earth's sun-heated surface material. The sun incoming infrared radiation does, however, directly heat the water vapor and the cloud, which are the fine water droplets in the atmosphere. Nitrogen and oxygen remove a high percentage of the sun's excessive heat from the Earth's surface to the cold upper tropospheric level via convection, where it is dispelled. The evaporative cooling of water from the Earth's surface also is one of the main processes by which heat is moderated, transferred, and transported around the Earth. We will now be looking into the movement of heat. The movement of heat. First and foremost, heat generally moves mainly in one direction, and that is upward and away from the Earth's heated surface, mainly by conduction, evaporative cooling, convectional current, and terrestrial infrared radiation into the atmosphere, which is eventually dissipated. It also moves laterally in a limited basis, which is trapped in an heated air, when it's trapped in the heated air mass, and move over the land via the convectional cycle. It also moves lateral sometimes when it is given off as terrestrial infrared radiation. Eventually, however, this lateral heat movement will also be directed upward or vertical into the upper troposphere for dissipation. Heat also, on a limited basis, penetrates downward by conduction when the heat is Earth's surface, such as land and water, are being directly heated by the incoming sun infrared radiation. This downward movement of heat is also dissipated the further you go from the surface and deeper into the Earth's surface away from the sun. And as you can see from the diagram, where heat is generally moved upwards, we show a match being lit, and we see radiation coming off, convectional hot air rising, cool air coming in, and being heated and moving upward. And we also see where conduction is heat from the head of the match is conducted away from along the stick itself. So in this way, it shows that heat generally wants to move away from the hottest source, but generally it moves in an upward direction. We will now look at how heat and temperature are related. Scientific properties are important to climate change, to the climate change discussion or debunking. The climate change controversy is all about how heat is trapped in the atmosphere. What this does imply that the Earth has a deficiency in regulation of heat. This is what the climate change alarmists are claiming, that Earth has a deficiency in its regulation of heat. This presentation is to totally and absolutely debunk this notion. Therefore, it's important for us to have an understanding of the dynamics or movement of heat as it is created, moved around the planet, and in and out of the atmosphere. It's important to understand this dynamic before you start making claims that the Earth has a deficiency in its ability to regulate the heat. The study of this dynamic of heat is called thermodynamics and will play a crucial role in the process of debunking climate change due to the burden of fossil fuel. We will now be looking into the Earth thermodynamic drivers. What do I mean by thermodynamic drivers? Drivers that moves heat, that cause the movement of heat around the Earth, the surface of the Earth. And the movement of heat is governed by the following process: a pressure differential, a specific heat capacity differential, a thermal conductivity differential, density differential, temperature differential itself, altitude differential, latitude differential, and phase differential, meaning changes from solid to liquid, liquid to gas, which is important in water. This change in from liquid to gas to water to solid in water is very important in the transfer of heat and the movement of heat around the Earth. These are I will in this presentation I will be concentrating mainly on only two of these drivers, two or maybe three of these drivers, and we'll be looking at specific heat capacity differential, thermal conductivity differential, and phase differential. These are the ones that we will be looking at in detail, a little bit detail in this presentation. The other ones will be mentioned but not taken into any great detail. Of all the aforementioned thermodynamic properties, the two that is the most important will be examined in this slide. Of all the available thermodynamic properties, the one that will be most effective at ending this debate about climate change due to the burden of fossil fuels are as follows: specific heat capacity of a substance and the thermal conductivity of a substance. These thermodynamic properties will tell us exactly how much heat an individual substance can hold, how fast it heats up and cools down, the rate at which it transfers heat, the substance's willingness to transfer heat to or absorb heat from the surrounding environment. So these are two important thermodynamic properties that we will be concentrating the rest of the videos on. We will now look at the reason, answer the question as to why is there so little known about these two thermodynamic properties. To be able to find and research these thermodynamic properties that we had mentioned before, namely specific heat capacity and thermal conductivity, on the internet, you would have to first be aware of them, and secondly, you would have to specifically input them into an internet search browser to get the information. Information does not freely expose you to these specific scientific physical properties. These properties are usually only exposed to individuals who have a very specialized, who are in a very specialized field, such as engineers and scientists. The specific heat capacity and thermal conductivity tell us how effectively a substance is at capturing, holding, controlling heat, characteristics that would be very important on the subject of climate change. By knowing and understanding them, we intuitively get a deep and sound understanding of how many of life, nature, and climatic processes works. These thermodynamic properties were purposely shadow banned because with a general knowledge and understanding of them, those who are perpetrating the climate hoax due to the burning of fossil fuel knows that they would never have gotten away with it. So as you see from my drawing, the specific heat capacity is quite simply a measure of how much heat or thermal energy a specific amount of substance needs to change its temperature by 1 degree Celsius. And as you can see from the drawing, when you add heat to a specific amount of material, the temperature will change from T1 to T2. So therefore, the higher the specific heat capacity, the more heat it can hold or trap per molecular mass, and the less its temperature will change with the addition of this heat or thermal energy. Organic material tend to have a higher specific heat capacity than metallic material, and tend to heat up and cool down slower than metals. For example, water has the highest specific heat capacity of all liquid, which makes it a good moderator and controller of temperature. In regards to the atmospheric constituent, the specific heat capacity is therefore a good scientific measure of how effective each constituent are at trapping heat in the atmosphere. Therefore, the higher the specific heat capacity of the gas or component, the greater its greenhouse potency. Here we now have a look at the specific heat capacity range or grouping for all the relevant environmental matter. And as you can see from this comparative analysis of a breakdown between the Earth environmental matter, they are grouped in various spheres. Water is called hydrosphere, organic matter is called biosphere, the air above us is called atmosphere, and inorganic abiotic matter is called the lithosphere. And they are ranked from the highest to the lowest in regards to specific heat capacity. As you can see, water has the highest specific heat capacity of all the environmental matter, and it followed by organic matter, and then last is abiotic inorganic matter. What this comparative analysis shows and tells us, it dictates actually the movement of heat between the various spheres of the environmental matter. So during the day, when the sun is up, the Earth's abiotic matter, the land, eats up substantially faster than any of the other tree sphere above it. So most of the heat produced from by the sun is quickly transferred into heat by the inorganic matter on the land, and this excess temperature is transferred into the atmosphere, mainly into the atmosphere, and warm the atmosphere. So this is what happens during the day. During the day, because of the water have such a high specific heat capacity, it slowly warms. It slowly warm at a rate much slower than the land surfaces, and this is what causes the phenomena of land breeze and sea breeze, which is reversed during the night. So during the night, when the sun goes down, again, the abiotic matter, inorganic matter, cool on much faster than any of the other above, and therefore there's a reversal of temperature of heat that is moved from the atmosphere to the land, to the abiotic matter, which now becomes a heat sink. So this difference in specific capacity dictate the dynamics of heat between the various spheres, um, between day and night, and winter and summer, and dictates a lot of the movement of heat in and around the Earth's surfaces. So here is a hand-drawn diagram that I've made that tries to explain as simple as is possible what thermal conductivity is actually. So quite simply put, thermal conductivity is a measure of the rate of heat transfer across a specific width of a specified substance. It is thus primarily a measure of a substance's ability to transfer heat, and secondly, its ability at releasing, trapping, and/or holding heat. Solids tend to have a higher thermal conductivity than liquid, which tend to have a higher thermal conductivity than gases. This is because of the increase in distance between molecule and atom as they go from a solid to a liquid to a gas. Every substance in Earth has a well-documented thermal conductivity rate. For instance, styrofoam has a thermal conductivity of 0.011010 watt per meter Kelvin, and iron has 75, which is much higher. Conductors therefore has a higher thermal conductivity than insulator, as they heat up and cool down faster and trap less heat than insulators. In regards to gases, which tend to have the lowest thermal conductivity, it is thus a good measure of how effective a gas is at trapping and holding heat, which is a good measure of the greenhouse effect in the atmosphere. We will now have a look at the thermal conductivity range for all the relevant environmental matter. And in this comparative analysis, you can see they are grouped again in regards to the air, which is the atmosphere, organic matter, water, hydrosphere, and inorganic matter, which is the lithosphere. And in this time, the thermal conductivity is ranged from the lowest to the highest in terms of a range. What is important to note from this comparative analysis is that the air, organic matter, and the atmosphere all have thermal conductivity range which is way below 1. And as you can see, inorganic material have a thermal conductivity range. We start at 1.08 and go all the way up to 2,200 thermal watt per meter Kelvin. This shows that inorganic material with such a wide range of our thermal conductivity and with such a high level of thermal conductivity is actually the Earth's driver of heat. It means that it passes through inorganic material, allow heat to be transferred very quickly through its surface, allowing it to heat up and transfer it away from itself to any other material that engulfs it. And the nearest material that engulfs inorganic material is the atmosphere. So during the day, when the sun comes up and the infrared radiation causes the inorganic material to heat up, the excessive heat is actually pulled away as fast. It's actually spread fast into the rock itself and inorganic material itself, but it's also transferred fast from these materials to the air via conduction and then eventually convection into the atmosphere. So the Earth inorganic material with low thermal conductivity, with its high thermal conductivity, actually is the Earth temperature driver, the main Earth temperature driver. The other three environment material which with low thermal conductivity tend to be, and these also have higher specific capacity, and they also tend to have higher a better moderating of temperature than the inorganic material. We will now be looking at the role that the atmosphere play because of its very low thermal conductivity. The low thermal conductivity of the atmosphere is instrumental in the following natural phenomenon: formation of distinct air mass of different temperature, density, and humidity. 2. The preservation of heat in the lower layers of the troposphere and the Earth's surface for the sustainability of life on Earth. The controlled loss of heat to the upper troposphere to prevent too much excessive loss, especially during night and winter conditions, again for the preservation of life on Earth. And 4. The production of varying weather conditions such as rainstorm, as these different air masses interact with each other along what is called fronts. The weather systems they produce provide a very swift and drastic means of removal of rapid, dangerous heat buildup in the lower troposphere, where huge volume of very hot air and humid air mass is forced upward into the colder, higher troposphere atmosphere, where it condenses as rain. And here you see a picture of some very distinct air mass, and as you can see, this is over the United States, and all these air mass eventually interact with each other to produce many different forms of precipitation and weather system. As you can see, you have the further north, you have the continental polar here, which is cold and dry. You have the maritime polar here, which is cold and humid. You have also, and then further south, you have the maritime tropical warm, which is warm and humid. And inside the continent itself, of the country of North America, the continent of North America, you have the continental tropical, which is hot and dry. So in this slide, we'll be looking at the role or the function of the atmosphere in regards to the climate. The function of the atmosphere in regards to the climate. So, in regards to the climate, the atmosphere plays two very important life-sustaining roles, and they are as follows. During the day and summertime in temperate climate, the atmosphere plays the role of the removal of excessive heat from the surface of the earth, mainly through the process of evaporative cooling, conduction, and convection, taking the heat away and disposing it to the coldness of the upper troposphere. The heat is the sun is the driver of the convectional current and evaporated cooling. 2. During the night and during the winter months in temperate region, the atmosphere reverse role reverse to one of trapping and conservation of heat, moderating the rate of heat loss to the cold upper atmosphere, troposphere, until the sun comes up the next day or summer comes around back again. Does the earth remove excessive heat? During the day, mostly in the tropics and during summer in the temperate region, the excessive and relentless heat produced by the sun on the earth's surface material is removed via two important methods. First is the water cycle, where we have the evaporative cooling and the condensation, taking water up to the cloud level where it's condensed and released, and is absorbed by the nitrogen, oxygen, and is taken further up into the cold troposphere. And second, by the convectional air current that is mainly consists of nitrogen and oxygen, absorbing the heat from the Earth's surface directly by conduction. And then thirdly, all the Earth deal with excessive heat is by the sea and ocean current. These three systems work together to safely remove heat buildup that would threaten life on Earth as we know it. And how does the Earth preserve heat? We'll be looking into how the Earth preserve heat. So during the night and during the winter in temperate climate, when the Earth's surface fails to receive sufficient infrared radiation, the Earth converts into heat preservation mode by the following. 1. Trapping a warm blanket of in the low atmosphere air mass just above the Earth's surface that protects the surface from the extremely cold upper troposphere air mass, as air mass of different density does not readily mix with each other. So there's a buffer, warm buffer zone that is preserved lower near the surface of the Earth that does not mix. As the Earth's surface cools down faster than the atmosphere, there is a net heat transfer back from the atmosphere to the Earth's surface overnight, as the Earth's surface now becomes a heat sink. This movement of heat helps to moderate the rate of cooling of the Earth's inorganic materials. Number 3. Water vapor and cloud in the air plays an important role in preserving this warm air mass, especially in the winter. As during the day, the clouds and water vapor in the atmosphere is still directly heated by the sun's solar radiation, whereas nitrogen, oxygen, and carbon dioxide gases are not. Finally, the heat in this warm blanket slowly bleeds off and becomes thinner as the night progresses, just in time to be replenished by the sun the next day. So this is 3 ways in which heat is preserved on the Earth, as we go from night to day and winter to summer to winter. In this slide, we'll be looking at the water cycle and how it rotates heat and transfers heat around the Earth's surface. The water cycle is known to most of us and involves the evaporation, condensation, and eventually precipitation of water with the enormous transfer of heat and heat between the various phases of water. It is a very high specific heat capacity of water that accounts for its ability to perform in this very vital function in heat maintenance of the Earth's surface and atmosphere. This latent heat is removed from the Earth's sun-heated surface up to the cloud altitude via evaporation and is released when water condenses into clouds. This released heat is then absorbed by the surrounding nitrogen oxygen gases at that altitude and is taken further high up into the cloud troposphere level for disposal or for absorption by surrounding water droplets in the clouds. When rain falls, which is called precipitation, the water is generally much cooler than the Earth's surface temperature and thus also have a cooling effect. It is important to recognize the role that water vapor and clouds play in climate change. So as you can see, the volume of water in the cloud droplets in the sky is equivalent to the amount of water in the river on the surface of the Earth. Pretty interesting, huh? Water vapor can vary from 0.02 to 4% total of the atmospheric gases. Cloud and water vapor are blown around by high-level winds in the skies. Depending on where the clouds are, they can by dynamic change from water vapor to cloud droplet and back again by the combination of solar energy radiation and the height at which they are located. Cloud and water vapor hold and traps a very large amount of heat in the atmosphere. As you can see from the right, the process where the sun warms a water source. Evaporation occurs, creating moist, warm air. As the air rises, it cools. When it cools to the dew point and below, the water vapor condenses into tiny droplets called cloud condensation nuclei. Cloud condensation nuclei can be smoke, dirt, or smoke. Most clouds are composed of water droplets, but very high altitude clouds are composed of ice crystal. So it is important to know that the important thing here to walk away with is that cloud and water vapor hold and traps a very large amount of heat in the atmosphere. Here we'll have a look at the convectional air cycle. And as you can see from the diagram on the right, heat is absorbed via conduction from the sun-heated surface. It is taken up to higher altitude via convectional air current, where the heat is dissipated to the cold upper tropospheric level. The cold air molecules then return to the Earth's surface to repeat the process. We will now have a look at the worldwide convectional current. The Earth has three equivalent convectional air cycles, north and south. One convectional cycle per tropical, temperate, and polar regions. Each take heat up to great height in the troposphere to dispose of it. The red line represents the heated air and the blue line represents the cooled air. And as you can see, the Earth is divided into three equal polar cells, and the air meet at the polar region, the Earth's latitude, and the intertropical convergence zone that gives rise to the trade winds, the westerlies, and the polar easterly winds. Here we'll have a look at another of the thermodynamics, thermodynamics that take place importantly in the Earth surface. So in here we'll be looking at the heat distribution via sea and ocean current. Very important. The distribution of heat around the Earth's surface via the sea and the ocean current is of the utmost importance also in preserving life on Earth. Just as we look at the heat transfer between the surface and the atmosphere, we now be looking at the movement of Earth, of heat around the Earth's surface itself. And this is one of these methods is in the sea current, the movement of sea current. This is possible with water having the third highest specific heat capacity of all substance on Earth, and is very good at holding a huge amount of heat for a long period of time. Water is also comprise 70% of the Earth's surface, which make it a very moderating substance. Most of the heat is absorbed mainly in the equatorial region and then move north and south with the tides, spreading the warmth to the colder, temperate, and polar regions. A perpetual cycle is present when an extreme amount of high volume of water is moving from the equatorial region to the polar regions and returning via deep underwater current, as illustrated by the diagram to your left. So you see the warm water move on the surface. It is dissipated as it moves to the north, to the poles, where it transfers the heat, becomes cold, and cold water sinks just like cold air sinks, and it moves under earth, under the deep water, and again towards the equatorial region where it's warmed as it rises and meet the sun energy. So what are the obvious conclusions we can draw from this presentation that can be used to debunk climate change using thermodynamics? They are as follows. The Earth has a very effective thermodynamic system in place with many thermostatic processes for controlling, preserving, and distributing the heat it receives, from the sun, ensuring a range of temperature is maintained in which life can survive. Very important. Very effective thermodynamic system. Heat transfer to the atmosphere does not progressively build up over time, as the climate alarmists would have us believe, but flows between a well-defined range. A range that can vary a little bit to the left or to the right as time goes by, but it does has a definite range. Heat buildup is temporary and is short-term in nature, but is eventually released and dissipated as days turn into night and summer turns into winter in a perpetual cycle. Heat loss is also temporary and short-term in nature and is eventually replenished as the night turns into day and winter turns into summer. The phenomenon of weather is in place to adequately relieve any rapid and dangerous temperature buildup on the Earth's surface and the atmosphere immediately above, as long as sufficient amount of water is present. This rapid cooling method can be volatile at times, as seen in thunderstorms and hurricanes. And finally, the Earth is managing the heat it receives from the sun in an effective manner and will not lead to any existential threat to mankind. The heating is not of any existential threat to mankind. That is the most important thing. There's no existential threat to mankind from the Earth effectively managing heat and temperature. And I would like to take this opportunity for thanking you all to take the time to watch this presentation. I hope you found it as entertaining as it was informative. And keep on learning, keep on being curious, keep on researching. Knowledge is power.